Hello and welcome to Week 2, Lecture 1 of CO442642 Graph Theory. Today we'll be doing an informal proof of Brooks' theorem, the classical theorem that we talked about last week and stated, but now we'll be beginning the proof. So let me remind you what the statement of Brooks' theorem is. So here's the theorem from Brooks, 1941. If G is connected, then chi of G is at most delta of G if and only if G is neither complete nor an odd cycle. So again, this was improving on the greedy bound of delta plus 1 by getting rid of that plus 1 in the exceptional cases of being complete or an odd cycle. If we forbid those, then we can get down to chi being at most delta. So that was the statement of Brooks' theorem, and we had done the motivation in the introduction to coloring last week. But now we'll be beginning the proof. So how to prove Brooks' theorem? How to prove this classical theorem? Well, amazingly, there are actually many different proofs, arguably 8 to 10 distinct proofs of Brooks' theorem. So I would recommend to you the very nice survey by Cranston and Rayburn from 2014 for more details. But here's a selection of the various methods one could use. Greedy coloring, which is what we'll be using today. Kemp chains, which we'll see next week with Vissing's theorem. List coloring, which you've already seen a bit in the homework and we'll also revisit. The Alon-Tarski theorem, kernel perfection, or the potential method, just to name a few. So many different ways to prove Brooks' theorem, but today we'll just focus on one. The greedy coloring approach, which we already introduced last week, wherein you order the vertices and greedily color. So again, the purpose of today's lecture is to just give an informal proof sketch of Brooks' theorem. Next lecture, we'll instead go toward a formal proof, to take our informal proof sketch and convert it into a formal proof. But today we're just going through the ideas. So for this informal proof sketch of the greedy coloring method, and I just want to say that arguably why did I choose the greedy coloring method? So for the Kemp chain proof, which is also very nice, I refer you to Diestel, but the greedy coloring method is arguably the most direct and brute force of the approaches. And so it's, in some ways that's very natural. Just taking the very base elements, the most instinctual way to prove the theorem. So let me try to describe it. So you already know the greedy coloring method, but let me be a little bit more holistic. So the idea that is the key to this approach is we're trying to combine a method, greedy coloring, which we already know works for a similar problem, the delta plus 1 coloring. We use this greedy ordering to delta plus 1 color graphs, and that's very similar. Here we're just trying to save the 1. But we're going to ask under what conditions can we use this to get the desired outcome, a delta coloring, right? So if we have a method we know works for similar situations that works pretty well, maybe we can just use it and tweak it and see under what conditions can we still use it, and maybe then we can figure out ways to handle those other cases. So in the other cases where we cannot apply greedy, we instead do the following. We use reductions. That is, we show how to inductively color, or we show that the graph is one of these exceptional outcomes, a clique or an odd cycle. So this is a very general way to attack problems. Use methods that you know to handle various cases, and for the ones that don't, maybe look for reductions. Look for ways to reduce the problem, use minimality, use induction to handle those, and finish off certain special cases. So how else can you think about this? Well, alternatively, we could have built up a suite or library of reductions that work, and then try to find a method to deal a finishing blow, to handle the cases we could not reduce, right? So I want you to think, I said before, is you start with a similar method and then you get reductions to fill in the gap, but maybe it came about the other way. Maybe instead you first figured out a number of reductions that you could use to do the proof, and only then you try to find the blow that will finish it off. So all that's to say is, either way, this is a mashup of reductions and some finishing blow. And it's an art form, it's not an exact science. The goal is to have these two halves of a proof meet in the middle to complete the proof. And sometimes that works. Sometimes you even get more than you need on both sides. And they could do it kind of meet here or meet there. On the other hand, sometimes this doesn't work, and you fall a bit short, and this doesn't end up leading to a proof. But in general, it is a desirable proof strategy to use what you know and standard reductions to complement that. So that's our greedy coloring approach. Let's go through. So today, instead of starting with the greedy approach and the method and reviewing under what conditions that will work, let me instead focus on some reductions. So let's imagine we're going to build up a suite of reductions and then see where that's useful to finish the proof. So here's a first reduction we could try. We know the graph is already connected, but let's ask what if it has a cut vertex? G has a cut vertex V. How to use this to our advantage? How to use the fact that it's a cut vertex? So maybe imagine for yourself a moment, maybe draw a picture of a generic cut vertex and label the graphs it cuts into and do that. Well, actually, I went ahead and did this for you. Then V separates G into two smaller graphs, G1 and G2, somewhat as depicted. So this is just a very generic picture, but maybe it can help give some idea. Now what do we do? Well, the point is that these graphs are smaller, as bolded. So then by the minimality of G, if we're going by, say, minimum counter example, then each Gi will have a delta coloring Phi, I, and 1, 2. Okay, that could actually be a lie, because technicality, again, we have exceptional cases. This only works if the GIs are not the exceptional cases. So k delta plus 1 or an odd cycle when delta is 2. And as an exercise for next lecture, where we're going to actually do the formal proof, you can think about why can we assume this? So why is this true? What's the argument why neither of these is actually an exceptional outcome? But for today, I'm not going to give you the answer to that. I'll just let you think about it. So this is a technicality to check the conditions, but actually it ends up working. There is an argument. Okay, so we have these colorings, then what? Well, maybe they don't quite agree, but there's an easy trick is to permute the colors. So you could say permute the colors of Phi2 so that they agree on V, so that Phi1 of V is equal to Phi2 of V. And then if you just take the union of the colorings, you'll end up with a delta coloring of G, which is a contradiction. So that's how to handle cut vertices, modulo the technicality why G1 and G2 satisfy the conditions and aren't exceptional. What else? Well, there's a second reduction we can try, which is having a two-cut. So two vertex cut set, U and V. And well, how do we use this to our advantage? Maybe pause a moment and think. But again, it's the same trick. We're going to take UV and separate G into two smaller graphs, G1 and G2. And again, by induction or minimum counter example, so here we're doing minimum counter example, each of G1 and G2 has a delta coloring Phi, where I is in 1, 2, right? So we have these two colorings, but the question is, can we still glue the colorings as we did before to get an overall coloring of G? Well, that's a good question. Well, if the edge is UV, if the edge UV is in E of G, then we can actually permute the colorings so that this works, because then U and V will have different colors, and then we can just make sure that Phi1 of U is equal to Phi2 of U, and Phi1 of V is equal to Phi2 of V, and the proof will go through modulo, again, the technicality why G1 and G2 aren't exceptional. So the bigger question is, do you see why this fails if UV is not an edge of G? So I would encourage you to pause the video a moment and come up with the answer why this gluing approach might fail, this permuting approach, if the UV is not an edge. All right, so for those who figured it out or just want to enjoy the show, we have, because U and V could be colored the same in one coloring, so they could both be 1, say, and different in the other, say 1 and 2. And no permuting will fix this, right? You can't permute colors so that different becomes same. So what do we do? What to do? How do we solve this issue? We had this very nice approach about cut sets, but it got harder with larger cut sets. So what is the option to do? So maybe pause and think a moment. The answer is add the edge. Add the edge UV to both G1 and G2. So here's a little picture. So now we're in the case where you don't have the edge, right? If there was an edge, everything worked nicely because we know they're different and you could just permute to match. So here's the trick. You just go to that case. You kind of reduce, or rather you up yourself to that case. So we take G1 plus UV and G2 plus UV to do induction or minimality of counterexample on, and then we get colorings and glue them. But again, there are technicalities, right? One is we have to show that the maximum degree is not actually larger than the original maximum. So when you add the edge uv, that delta of g1 plus uv and delta of g2 plus uv, that they're not bigger. And how can we argue this? So again, this is an exercise for next lecture when we do the formula proof, but maybe think for a moment or pause and kind of come up with the answer for this and how would you do it if you want. So there is a way to do it, and again, that's just a technicality. So why, this is again a condition of the theorem, so why can we do that? And yet there's another technicality, which is the same one, is we also have to ensure that neither G1 nor G2 is complete or not cycle in the delta equal 2 case. And again, exercise for next lecture, how can we ensure that technicality? How can we ensure, what argument can we use? And this one's a bit trickier than the last two, so maybe pause and think again, but we'll cover that somewhat more complicated reasoning, but there is an argument one can make to ensure this. And because maybe it's not actually possible, but if you think about it, if you think maybe there is a way to more cleverly choose the u and v to force this. So that's it for the two cuts and the reductions. Let's go back to applying greedy. So now if we've gotten rid of cut vertices and two cuts, we can assume the graph G is 3 connected. It's not yet clear why that's useful, but we now turn to our finishing blow, greedy. So question, when does greedy fail? So throughout these informal proofs, I'll be asking bold questions with a Q there to kind of prompt you to answer. And again, so you can pause the video and come up with the answer yourself, and then we'll come back and we'll answer it. So sometimes I'll just ask more open-ended questions, which maybe you won't be primed to answer or will be a bit more subjective in their answers. But here, you should maybe be able to figure out, when does greedy fail? What would be the conditions? So coming back, the answer is when a vertex V has delta of G earlier neighbors in the ordering, and each of these get some different colors. So here's an example, a picture, V, and it has earlier neighbors if you're doing left to right in the ordering, colored 1, 2, up to delta of G. And again, those don't have to be colored in that order. It could be delta G first, then 1, then 2, etc. But it sees all the different colors, so when it goes to by greedy to get its own color, it has none left for itself. That is the only case where a greedy algorithm would fail at such a vertex. So the question is, can we avoid this, right? Can we find an ordering where most of the vertices have at most delta of G minus 1 earlier neighbors? That would seem useful, right? We need to have actually delta earlier neighbors to end up in this problem of failing. So if we could avoid that, at least for most vertices, then that would be useful. Of course, we can't do it for all, because how else could you then be able to color the clique greedily? So it has to fail, but maybe it only has to fail at one vertex. So think about it. And the answer is, as I hinted, you can do it, yes, for all but one, but actually for all but the last vertex in the ordering. It is possible. So it is possible. And the question is how? So again, I ask you to pause the video and think, how would you make an ordering where all but that last one have at most delta minus 1 earlier neighbors? So maybe you know this. The answer is fix a root and take a depth first search tree ordering from the root. And then you flip it, you reverse it. So here's a picture. So we have some depth first search tree of our graph. So maybe our graph isn't a tree, but we just found it's connected. It has a spanning tree. So you make it a depth first, you order it from the root 1, 2, 3, 4, 5, 6 there. And then we take that and we reverse the ordering. So we put the root at the end and then 2, 3, 4, 5, 6, but in reverse order. And you'll notice that this reverse ordering has the nice property then that every vertex, except for maybe the last then, but every other vertex has at least one later neighbor because of the depth first search tree. And so it has at most delta minus 1 earlier neighbors. Now, of course, the last vertex will have delta earlier neighbors, at least if it has degree delta. So we can't avoid that. But now at least all the vertices but the last one will be fine and greedy. They'll only see at most delta minus 1 colors, and so we will be able to go well until we get to that very last vertex. So how do we save the last vertex? Can we ensure greedy does not fail at that last vertex V? So again, pause maybe and think for a moment. Well, there's a good case It's if the degree is at most delta minus 1, right? Then you'd be fine. Then it would have a color left. So actually, the bad case is having degree delta. And here's the idea. If only we could ensure that two of its neighbors, x and y, are colored the same. And hence that there's a color left for v, right? The only bad case was it had delta earlier neighbors, and they were all different. So guaranteeing two to be the same would fix the problem and finish the coloring. But here's the question, which two? Which two neighbors x and y should you pick? Well, think for a moment. Again, you have to be non-adjacent to get the same color. And how do you know that those exist? Well, they're guaranteed to exist because G is not K delta plus 1. So you have delta neighbors here, and you know at least two of them are not adjacent. Otherwise, you'd have a K delta plus 1, and that's an exceptional graph. So because we're not exceptional, because we're not the clique, we can get two non-adjacent neighbors, x and y. Okay, good. But how do we guarantee that they're colored the same? I mean, if they're somewhere in the middle of the ordering, the colorings may just be forced upon them, and they may end up with different colors if we're going by greedy. So pause and think for a moment, how could we force them to be the same? Well, the answer is to put them first in the ordering. So right, if we put x first, it comes first before anything. There's no restrictions on it, so we can color it whatever we want. We could color it 1. What about y? Well, if we put it second, so if we put them both together as the first two in the ordering, well, y isn't adjacent to x by assumption, so it also has no restrictions, no earlier neighbors that are colored, and so we could also color it 1. So we can color it the same as x. So this is the key. We could put x and y first in the ordering together, and then we get to choose what their colors are, so we can choose them to be the same, and then continue on with greedy, and everyone else should probably be fine, and then we'll get to v. But there's some questions here. How do we finish the ordering? So every vertex in what remains outside of v, x, and y has at most delta minus 1 earlier neighbors. So we want v to be last, x and y to be first. How do we get the rest of the ordering? So pause and think for a moment. So how do you do this? Well, it's the trick we already learned. You use the reverse of a depth-first search tree ordering, but here we have to delete x and y. So we've already fixed them. So we order everyone else with root v. So g minus xy with root v, we take a depth-first search tree ordering of that and we reverse it. And that will fill it out. But that leaves one last major question. Why does this ordering exist? Right? We knew before if x and y were also part of this tree that it existed because of the connectivity, but why does this exist? Right? If we're going to force x and y to be first, maybe it doesn't. So pause for one last time and think about why this is the case. Why now do we know that this ordering actually does exist? All right, so for those who got it, the answer is, well, g minus xy is connected, right? So it is connected when you delete x and y. The reasoning is that g is 3 connected. So when we delete two vertices, here x and y, it remains connected, and then a connected graph, of course, we can do a root and we can do this depth for a search tree and then reverse that ordering. So that's the reason this all works. We used our reductions to get rid of cut vertices and 2 cuts to get it to be 3 connected, so we could, in essence, build this very nice ordering. And again, they're 2 peas of the same pod. We could build up the reductions and then figure out how we could use them, or maybe the other way to think of the proof is we maybe started with greedy, realized that those were the conditions under which it worked, asked how we could guarantee, how we could build these nice orderings, and then realized if only we knew the graph was 3 connected, then it would be easy and we could just get the ordering and be done. So then we look to cut vertices and 2 cuts and ask how can we reduce those cases. So here we finally meet in the middle and we complete the proof this way. So again, this is just an informal proof sketch. Next lecture, we'll be talking through a formal proof. So formalizing this, dealing with those various technicalities that I left out and left as an exercise for next lecture. So please go back through those if you want, or tune in for the next lecture to figure out the answers to those questions, while we also spend a bit of time on writing and formalizing a nice written proof of Brooks' theorem using this greedy coloring approach. So that's all for today. Thank you.